So I want to write you the square function as the Fourier sum of sines and cosines, and for that I have to find myself these amplitudes AKs and BKs, and my function is the f of x, the square function. It's minus 1 between minus pi and 0, and it's 1 from 0 to pi. And let me draw you this, how it's going to look like. This is x, this is f of x, and somewhere here minus pi, this is pi. So it says it's minus 1 when you go from minus pi to 0, so it's minus 1, and it's 1 when you go from 0 to pi. And so this is how it looks like, and this is a periodic function. It will be repeated after 2 pi period, like this. And so let me do that for you. This is how it will go. Goes backwards to like this. And so we call this a square function, a periodic square function. Before I dive in finding you these amplitudes, I want to talk about the idea of even and odd function, because they might help us. Sometimes they help us save us from unnecessary calculations. So if I have a function like this, let me call it z of x. If the function's value at x is a, and function's value at minus x is again a with the minus sign, we call it odd function. And sine waves are odd. This is how they go. And so sine waves are odd. And you can also check that for this point, if at this point the function's value is b, then at the mirror image of that it must be minus b. I can take you one more function like this. So this is x, and this may be h of x. And if the function's value at x and function's value at minus x are exactly the same, maybe a, then we call this function even function. And cosine waves are even. This is how they go. They are symmetric beyond the wall. So cosine waves are even, and you can also do that for this point. They must share the same value, maybe minus b. And so what's the use of them? Well, since our square function is odd, this is odd, look, at this point it's plus 1, and at this point it's minus 1, so it's odd. When I write its Fourier series, only sine waves are going to participate, because sine waves are odd and this function is odd. So it's like an odd function can create another function, another odd function. And so sine waves are going to construct us this square function. There will be no cosines because cosines are even, and so you won't see them anywhere. And of course this integral will show you that AKs will be 0. It will tell you that the amplitudes for all the cosines that we can have in the series will be 0. And so the Fourier series for my function will only contain the sine waves, no cosines at all. And last time I forgot to tell you one thing. I forgot to tell you the interpretation of A0. A0, this integral, gives you the average of the function over that interval 2 pi. It gives you the average height of the function from minus pi to pi. So it gives you the average of the function. So if you take this integral first, it gives you the area under the curve. But when you divide it by 1 over 2 pi, it gives you the average height of this function over this interval 2 pi. And for this square function, it's really easy. When we go from here to there, look, function half the time it's minus 1 and half the time it's plus 1. So what's the average of this function over that interval, over that period? 0. So this will be 0, A0 will be 0, and all the AKs will be 0. All I am left with, BKs. That's what I have to find you. So I do not need them anymore. Now we can find this integral, it's no big deal. But there's one more thing. Focus on this product only for now. This is an odd function and sine waves are odd. Any sine you can pick, they are odd. And when you take two odd functions and you multiply them together, they produce an even function. And even functions are symmetric beyond the wall. So when you integrate it from minus pi to 0, this integral minus pi to 0 will be exactly the same as you integrate it from 0 to pi. And I can show you that very easily. If you want to find B1, you put k equals 1, the fundamental frequency, and when you multiply it with the square function, it's like, so let me do it here. It's like if I take sine of x, it's like fitting in a sine wave here, and now I have to multiply this sine wave with the square function. So I take this value of the sine function and I multiply with the square function, which is negative 1, and so negative times negative gives you positive, and it also holds for these points and all of those points. So what happens is this value flips over like this, and so this product becomes an even function. And look, so this mountain is exactly the same as that one. It means this area and this one all are the same. It also means the integral from here to there will be exactly the same as you go from here to there. And so what I can do is I can integrate it from 0 to pi. So you think of this these two mountains right here. So I can go from 0 to pi and I double it, just to make calculation a little more easier. That's why I did it. And you can also do it for sine of 3x when you put k equals 3 and when you multiply it with the function. And so let me do it here, and it will be very hard to make actually. So this is a sine of 3x, something like that. And you have noticed I have made these amplitudes a little shorter. I did that on purpose because when I was actually doing it before, the picture was becoming a little nasty. So think of these sine of 3x like going like this, all the way touching the square function. And if you now do that, these two values will flip over and this will come down, and again they become symmetric. So it works for any sine wave that you can choose. And so now I can solve you this integral. We are going from 0 to pi. We are going 0 to pi, and the function's value is 1. So I can put it 1 now, and now it becomes very easy. This is the integral of sine waves, and it gives you cosine wave, the integral, with the minus sign, of course. So this becomes 2 over pi minus cosine of kx divided by k, and you have to go from 0 to pi, and it's very easy to do. It's 2 over pi. When you evaluate it, it becomes 1 minus cosine of k pi divided by k. And look, I have found you the amplitudes for the sine waves, because all you have to substitute is the values for k, 1, 2, 3, 4 fundamental frequencies and higher harmonics, and I can do that. I will do that, and I will put those amplitudes in a set. So 2 over pi will be common, and let me do that in a set. So when I put k equals 1, the fundamental frequency 1, and cosine of pi is minus 1, and I already have a minus sign, so this becomes 1 plus 1 gives you 2, and now I can find you b2, so it becomes k equals 2, cosine of 2 pi is 1, so this will be 1 minus 1 gives you 0. And actually you could have predicted it already that this will come out to be 0, because now you can go back here with your function f of x, and you can take sine of 2x and you try to fit that sine of 2x wave somewhere here, and when you integrate it, you will look for the areas under the curve, and you will see the area under the curve will give you 0. Try that. It will give you 0. I will move forward with the k equals 3, and cosine of 3 pi is minus 1 again, and I already have a minus sign. So this gives you 0. And so this pattern will move on. Next term will be 0 over 4, and next term will be 2 over 5, moves forward like this. And these are the amplitudes that we were looking for. This is B1, B2, B3, B4, B5, and of course this is also the part of those amplitudes. And there's one more thing I can do. These 2's, I can take them out because they are common, so 1 left behind, and this becomes 4. And now I can take this and I have to put them into the series, into the Fourier series. That's what we wanted. So this will be 4 pi will be common. So first term is sine of x with amplitude 1. Then next term is sine of 2x with amplitude 0. So we do not need that. Then next term will be sine of 3x with amplitude 1/3. And next term will be sine of 5x with amplitude 1/5, and it moves forward like this. And I can write this in terms of summation, which is not really necessary, but let me do that. It is 1 over 4 pi and summation sine of nx divided by n, and this n goes from, starts with 1, then 3 and 5, moves like that, because amplitudes for 2, B2 and B4 and for even for that they are 0, so it goes like 1, 3, 5, 7, 9. And remember, this superposed wave I have already showed you in the opening of my last recording. And now I want to add next terms. Alright, I have fundamental frequency, sine of x, third harmonic, sine of 3x, fifth harmonic sine of 5x, amplitude 1, 1/3, 1/5, and now I am going to add 7th harmonic and 9th harmonic with them, and when you superpose them, this is the wave you are going to get. And this is not a square wave yet, but we are getting there, because now I'm going to add next 50 terms, and this produces the square wave. Beautiful, isn't it? Of course, some of the wiggles here, but it's oscillating around value 1, and this is oscillating around value -1, and that's what we wanted to have, +1 and -1. And now you might think, if I add more terms, we can get rid of these oscillations that we are getting here. Well, yes and no. It will surely become better in between, but at the edges you are still going to have these overshoots, and we call that Gibbs phenomenon. And it's really not the flow in Fourier series. It happens because our square function is discontinuous here. It has a jump. It's -1, and all of a sudden it jumps to this value, +1. And so derivative is infinite at this point. And we are trying to write the square wave in terms of sine waves. And sine waves, they have finite slopes. Sine functions are smooth. They go smoothly. Look, they go smoothly. They do not jump like this. Even together, these sine waves are not going to create an infinite slope for you right here. So these waves, sine waves, when they superpose here, they struggle to create a sharp corner. And so you do not get a perfect square wave. And why not? Maybe perfection is impossible. Now let me add more terms. There you have it. It becomes better. Now let me zoom in here, and I want to show you that I am still having oscillations there. And so look, still oscillating. And I can also show you here, still oscillations. But these oscillations are around +1. They are very close to +1 value. And that's enough for us. And we call this the square wave. It's a periodic wave. It will be repeated after 2π period. And there's a thing I can do. So let me remove some of the part. Oh, right. And let me draw that square function again. This was going like this. The function -π and π. What I can do now is I can take the integral of this function, and so when I take the integral of that, what's the integral of 1? Well, it's x. So I can draw you the integral function. It's x from 0 to π. This is how it will go. So this is π, and this height will be π2, and I can do that here too. When I take -1, it gives me -x. So this is how it should look like. This is -π, and this height is again π. And so this is the integral of this function. Let me call it z of x, right? Since I have taken the integral of a square function and I have created you maybe like a triangle function, because this is periodic, it's going to repeat like this. I can also take the integral of this series, right? So let me do that. So this will be 4 pi, and the integral of sine functions are minus cosine functions, so minus sign will be common, so this will become cosine of x plus cosine of 3x with 3 squared, right? When you take the integral of sine 3x, this 3 comes downstairs, so this becomes, and you already have a 3, so this becomes 3 squared. And next, and the minus sign I have taken that out already. And the next term will be cosine of 5x over 5 squared, goes like this. So this is the integral of that. But we are forgetting one thing, and that is the constant of integration. And so question is, what should be that constant? Well, take a0, take the average of the function, that's the best choice. And so how do you find the average of the function from this? So think of this as a square for now, and the water is filled here on these triangles between them, and now remove these stops out. What will happen? What will be the level of the water? Well, it will go right in the middle like this. Think about it. It will go right here at the level of pi over 2. So that's the average of this function. So a0 is going to be pi over 2, and of course the integral for a0, that integral 1 over 2 pi, the integral from minus pi to pi of the function dx will give you that. It will give you that for sure. And notice our triangular kind of function, this periodic function, is decaying faster. Look here we have the amplitudes 1/3, 1/5 for the third harmonic and fifth harmonic, but right here for the third harmonic the amplitude is 1/9, and for the fifth harmonic it's 1/25, right? So it's decaying faster. It means you don't have to keep many terms to create you this function, whereas here you will need many of the terms. It's because you have a discontinuity here, it's a jump function, whereas this goes smoothly. So it's easier to make a smooth function out of these harmonics with little bit of terms. We don't have to keep many terms. Now I want to talk about the Dirac delta function. So that's the second example now, and I hope you know about it and its property. So Dirac delta function is infinite at x equals 0, and it is 0 elsewhere between minus pi to pi. So between minus pi to pi it's 0, but at x equals 0 it is infinite. And so let me draw you that. So this is x minus pi, and right at 0 the function blows out. You have a spike. It gives you infinite. So this is the delta function. Black hole's singularity. Right at the center of the black hole the mass density is infinite. It's a delta function. Or you can take a point charge, electric charge. Since a point does not have the volume, the charge density right here blows up. It gives you infinite. It's a delta function. And notice this delta function is symmetric beyond the walls. It's an even function. So only cosines are going to be the part of this function. Only cosines. There will be no sine functions. And so the Fourier series will only have the cosine terms. And so let me first find you a0, and this sum goes from 0 to infinity, of course. And let me find you first a0, which is 1 over 2 pi, right? Yes. The integral from minus pi to pi of my function, the delta function, dx. And we are going to use now the first property of the delta function. This integral is the area under the curve of the delta function. I know it doesn't make sense, but it is the area under the curve. And this area is 1. It's 1. So what you are left with is 1 over 2 pi. And so how we think of that? Think of a very thin and very high rectangle with the area 1. That's how we think of Dirac delta function. It's 1, the area under the curve. And now I want to find you a case. So it is 1 over pi minus pi to pi of the delta function times cosine of kx dx. And now I'm going to use the second property of the delta function that says delta function is going to pick the value of the cosine function at the spike. And so at this spike, so it's x equals 0. When you put x equals 0, cosine of 0 is 1. So it goes away. Again, you are left with the integral minus pi to pi of the delta function dx, because this is 1. And so this entire integral becomes 1. And so you are left with 1 over pi. And so I want to explain it a little. So if you take your delta function and you multiply it with some random function, some ordinary function, maybe this function is z of x, then this product, when you integrate it from minus pi to pi dx, this product will be 0 everywhere. Right here, when you multiply them, it will be 0 everywhere because delta function itself is 0 everywhere. So it gives you 0. But at this spike right here, this delta function picks the value of our function right here. So it picks the value of the ordinary function at x equals 0. And this now can come out here, out of the integral, somewhere here. And now we are again left with minus pi to pi of that delta function, because that's the only value left of the function, of our ordinary function. Because delta function has already killed all the other values of this ordinary function because it was giving you 0. But right at this spike, this function, delta function, is going to this value is going to survive, because this integral will give you 1, because that's the property of the delta function. And so z, this survives, so this is 1, and we are left with the function's value at 0, and it could be anything. It could be 5, it could be 45, depends on your function. But in our case, this is cosine, right? And if I put k equals 1, if I take that, it's like putting in here a cosine wave like this. And now our delta function, so this is cosine of x, and now delta function will pick the value of the cosine function, cosine of x, at this spike, and right at the cosine at x equals 0, cosine of 0 is 1. So this is if you take that, cosine of 0 is 1. So that's what we are left with. So let me remove it. So all the cosines, all the frequencies, and all the harmonics are going to have the same amplitudes. Look, it doesn't matter now whether k is 1, k is 2, because it's a constant. So all the cosine waves are going to have the same amplitudes. And now let me put these two values into the series, and let me complete that. So it is going to be first 1 over 2 pi plus, and of course this will be common because AKs or ANs are the same. They will come out, and now we are left with cosines. Cosine of x plus cosine of 2x plus cosine of 3x, and it moves forward like this. And when I saw this for the first time, I was like, what? I mean, these are oscillations, and this is a spike all of a sudden. How in the hell this series is going to construct a delta function? And now I better show you this on the computer screen. It will make you sense. And so I have first harmonic cosine of x, second harmonic cosine of 2x, and both of them have the same amplitudes. Amplitude 1 over pi. And when I superpose them, this is the curve you are going to get. And I was quite sure that at x equals 0, they are going to give me a peak, because both the cosines at x equals 0 will give you 1, and I have divided them out by 1 over pi, so your peak value is 0.8 after the superposition. Now I'm going to add third harmonic, and you will notice this vertical scale, those numbers will change because this peak will rise up, and so to fit this picture onto the screen, this vertical scale will change. You will notice that. So third harmonic, and so this is what you get. And notice this curve is still broad around x equals 0. So I'm going to add first 5 harmonics, and you see more oscillations, and now your curve around x equals 0 is getting squeezed, and that's what we want. We want it to squeeze, we want it to become delta function. So let's do 25 terms. Here you go. The curve has been squeezed, and you are getting these oscillations, but those oscillations are dying. They are getting squeezed like this. They are decaying, so to speak. Now 125 terms, and look, we are getting something. Now we are getting something like a Dirac delta function. But look, this is funny. We are getting something downstairs. We are getting negative values for these two downstairs peak. And I don't know how to explain that, but this is the consequence of superposition. You will get them. So more terms. Do you want more? Maybe like 500 terms. And now maybe you want to call it a Dirac delta function, and the peak value is 160, and down below it's minus 30. I mean, imagine I have added 500 terms and still we are getting just 160, the peak. It's nowhere near infinity. But this is the idea. If you add infinite number of terms, cosine of waves at x equals 0, they will give you Dirac delta function. And now let me zoom in somewhere here to show you we are still having oscillations that you cannot see, but you will see now when I zoom in here. And now let me do that, and look, still getting oscillations. Looks like Asgard. And this Dirac delta function is periodic function, so it will be repeated after 2 pi period. So this is an approximation of the Dirac delta function that we write in terms of Fourier series.